Hello all. I just want to go over two trigonometric identities. They are at grade 11 level. They're not at grade 12 level, but I just want to show you how these identities are proved. So the first one, it says 1 over cos theta minus cos theta over 1 plus sine theta equals tangent of theta. So normally we start with one side and we reach the other side. Here, the right side is only tangent of theta, which is like a simple trigonometric ratio, and we can't do much with it. But the left-hand side is more complicated, and there's like two giant fractions with a subtraction sign in between, which means that we can subtract them. So logically speaking, we are going to start with the left side and not right side. So I write ls, left side, equals, I just copy exactly from the given trig identity, and then I start subtracting the two fractions. So when you subtract them, first of all, you have to find the lowest common denominator, which is cos theta times 1 plus sine theta. And then when you combine the two fractions, you end up with 1 plus sine theta minus cos squared of theta. This is how you subtract two fractions. You have studied how to add or subtract rational expressions in algebra. This is very similar. So now, in the next step, after we combine these two fractions, we subtract them. Instead of cos squared of theta, we use the identity 1 minus sine squared of theta, which is one of the famous Pythagorean identities. Cos squared of theta equals 1 minus sine squared of theta. So we are doing the substitution. But then there's a minus sign outside the bracket. So this minus sign has to be distributed. And in the next line, we get negative 1 plus sine squared of theta. Because negative 1 times 1 is negative 1, and negative 1 times negative sine squared of theta would be positive sine squared of theta. So in the next step, after we do the expanding, we notice that 1 minus 1, they cancel out each other. They add up to 0. Therefore, the numerator is left with only sine theta plus sine squared of theta. And then in the numerator, you see that sine theta is repeated twice. In other words, that's a common factor. So I factor sine theta out in the numerator. We end up with 1 plus sine theta inside the brackets. But this expression, 1 plus sine theta, is exactly the same expression that we have been carrying over from the top lines all the way up to here. Therefore, these two cancel out each other, meaning that their quotient is equal to 1. And 1 times sine theta over cos theta is equal to itself, but the ratio of sine over cosine is defined as the tangent of the angle. Therefore, the quotient equals tangent of theta, which is exactly the right-hand side we wanted to prove. So you see that in this example at grade 11 level, this is not grade 12 level, you see that first we combine the two fractions. Maybe in some other question there's addition of two fractions or subtraction of them. So we combine them, and then we use the trig identities we have learned in the past. So that's using previous knowledge. And then we use the expanding, comes from the algebra. And then we collect like terms. So 1 minus 1, it's 0. We simplify or collect like terms. And then in the next step, we factor out the common factor of sine theta. Again, we are using our previous knowledge of factoring, for example. We have learned it in the past grades. And finally, after we cancel out, we end up with sine over cos theta, which is another trig identity known as quotient identity, which is equal to tangent of theta. So you see, this is how we prove trig identities using past basic standard studied trig identities, or using algebra, whether it's adding, subtracting fractions, whether it's factoring skills, whether it's collecting like terms, whether it's distributive law we learned in grade 9. And putting all these things together, we prove that left side equals right side. Next example is right here. This time, let me read it. Sine squared of alpha minus cos squared of alpha equals a big fraction, secant squared of alpha minus 2 times tangent of alpha, cotangent of alpha, all over secant squared of alpha. When I look at this trig identity, I notice that the right side is more complicated, or that's what it seems to me. So I choose the right side. Here, I chose to start with left side to prove left side equals right side, as I did. Here, I choose to start with the right side and show that right side is equal to left side. So I'm writing the first line. I'm just copying it word by word. And then instead of cotangent of alpha, I use the reciprocal trigonometric identities, and I write 1 over tangent. It is a fact that cotangent is reciprocal of tangent. Now, tangent of alpha times 1 over tangent of alpha is going to be just 1. Any number times its reciprocal is equal to 1. Imagine 3 times 1 over 3 is equal to 1, isn't it? So we end up with basically secant squared of alpha minus 2, simply in the numerator. The denominator is secant squared of alpha. Now, instead of secant of alpha, I'm going to write 1 over cosine of alpha, because we know that secant is reciprocal of cosine. So I end up with 1 over cos squared of alpha minus 2 in the numerator. The denominator is 1 over cos squared of alpha. But then we always have the right to multiply or divide the numerator and the denominator of a fraction by a non-zero value. So assuming that cos squared of alpha is not 0, we multiply the top and the bottom by cos squared of alpha. And this is a nice trick. It's a nice technique, believe it or not, because cos squared of alpha in the numerator with cos squared of alpha in the denominator, they cancel out each other. So what is left in the numerator is only 1 minus 2 cos squared of alpha. In the denominator, we end up with 1 actually, because again, we're multiplying something by its reciprocal. So basically, the denominator is 1. I don't even bother writing it down. So we end up with 1 minus 2 cos squared of alpha. This is how far we've got so far. But then we are using an innovative technique here. Instead of 1, we can write sine squared of alpha plus cos squared of alpha. This is the most famous fundamental identity in the world of trigonometry. It's known as Pythagorean identity. We have proved it in the past. So sine squared of any angle plus cos squared of the same angle is always equal to 1. That means that instead of 1, we can substitute it with sine squared of alpha plus cos squared of alpha. But then we have negative 2 cos squared of alpha, which we can sort of collect like terms here, because cos squared of alpha minus 2 cos squared of alpha would be negative 1 cos squared of alpha. So we end up with sine squared of alpha minus cos squared of alpha, which is exactly the left-hand side we were trying to find. So that is equal to left side. We started with right side. We used trig identities. We simplified, we collect we didn't collect like terms. We simplified. We used the technique of multiplying the top and bottom by a certain expression, in this case, cos squared of alpha. And then we used other trig identities, Pythagorean trig identity, and then finally we got the answer. So basically, all the things you have learned in the past, you use them, all the skills you have gained, you use them to prove that right side equals left side. So these were 2 examples from grade 11 level, proving trig identities. And in the next lectures, you will see more complicated examples where we will be using advanced trigonometric identities such as compound angle identities or double angle identities, and we're going to be proving much harder trigonometric identities. Thank you for your attention, and one last advice: keep practicing. That's all.